Thanks for tuning into this talk. My name is Sandeep. I'm an incoming assistant professor at UT Austin, and I'm happy to share my joint research with NEC and Stanford on how we can rethink video delivery for machine perception tasks in cloud robotics. So today we're starting to see fleets of networked robots, ranging from low power delivery drones to this manufacturing robot, and even the Mars rover. And these robots are starting to see very rich sensory data, such as video or LIDAR. And they're starting to process this rich sensory data with extremely compute and power intensive models for machine vision, such as deep neural networks. And often they really want to rely on their local computational power. But if they're uncertain or see a novel video scene, they might actually want to query an accurate, but at the same time compute and power intensive deep learning model at a remote server. So a natural question to ask is, how should they represent, encode, stream, and transmit this rich sensory data to minimize bandwidth, but at the same time maximize their remote sensing task accuracy? And the key question that we ask in this paper is, if the downstream consumer of video is actually a machine instead of the human eye, what pixels matter to represent to achieve high sensing task accuracy? And the approach we take is information theoretic. So given a sensory input X, today in information theory, we would encode to Z, have a decoder to decode to X hat, and try to minimize the pixel-wise error or the mean squared reconstruction loss. And that's because the ultimate consumer is assumed to be the human eye, so more or less every pixel matters the same. But instead, if we have a deep neural network as the ultimate consumer, it might have a very different sensitivity to different pixels in a scene and only require a few pixels to get the essence of a scene in order to get a high task accuracy. So the approach we advocate in this paper is to use the task loss and use that to design or co-design how we learn how to represent, encode, and decode task relevant but salient pixels in a complex scene. And this will allow us to do efficient updates of HD maps and remote ML inference tasks in robotics. So the first contribution of this paper is to create a succinct mathematical problem formulation. As you see here, we want to learn an encoder and decoder in the broader objective of a remote inference task. So we start with the pre-trained task network. You could download this from several repositories or pre-trained models in green. And what is learnable in our problem is the way you encode and decode your sensory data to achieve high task accuracy. But not only do we care about the task loss, at the same time, we want to make sure that decoded inputs X hat are human interpretable in case you need to debug this sensory data in a remote server. So we regularize by adding a reconstruction loss objective. And our key contribution is to provide a mathematical framework and training algorithm to learn succinct task relevant representations. And this framework hinges upon the idea that we can analytically compute the sensitivity of the task input to pixel distortions, which guides the learning of an encoder and decoder. So for toy linear systems, as a motivating example, we are able to analytically prove what the optimal encoding decoding scheme for task loss should be, and it amounts to a singular value decomposition, or SVD. And our paper has these types of plots where we show on the x-axis the extent of compression, so how small our representation is. And on the y-axis, we show that we have low task loss for our system in orange, which is called TaskNet, as well as low reconstruction loss. So we show that our system also naturally gracefully scales to deep learning applications. We actually use compute efficient tensor processing units to do low power machine learning and vision tasks distributed between a robot and the cloud. And we see similar patterns here. We're able to flexibly split both robot and cloud computation and achieve lots of power and compute savings. And moreover, our approach generalizes to neural motion planning problems. We also hypothesize that focusing on actionable task-relevant pixels allows generalization to new domains. And we show this on an example of Martian terrain planning. So in essence, our problem and in this paper is on rethinking video delivery for machine as opposed to human perception. And if you have more questions about this topic, I'm happy to answer more during the interactive session.